Alright, so in this video here, part 8, I think, 7 or 8, I lose track. This is going to be purely testing the amp. Do what I call a no bullshit test. And what you're looking at now is I'm measuring the temperature at the top of the heat sink. I've been running this amp now, getting it ready for the tests. I wanted to let it run at a decent amount of power. It's running at about 12 watts, 10.5 volts output across an 8 ohm load, and been running it for about 3 hours. I was upstairs working, and it is really hot. So just wanted to show you top of the heat sink at the vent holes, about 150 degrees. Can't really touch it. Now, not that it would heat up like that under normal music conditions. This is steady state sine wave, but at 12 watts running steadily, it gets pretty darn hot. Okay, so what I have here, I'm going to try to breeze through this without too much talk. I have a little bit here and there, but I've written down here on this sheet of paper the specifications that are listed in the instruction manual. Power output, small signal bandwidth, damping factor, harmonic distortion, sensitivity, input impedance, and I forgot to transcribe the input impedance, but these are the specs from the manual, and I'm going to go ahead and try to measure these things. And yeah, it's either going to get a smiley face, as in it meets the spec, or it's going to get a pile of bullshit. So here's the no bullshit test, and we are going to get started with power output. First thing specified in the manual is that this amp puts out 50 watts channel, or it says actually greater than 50 watts, but 50 watts channel into an 8 ohm load. So to start with, I have my signal generator. That's my total harmonic distortion analyzer, as well as a voltmeter and a frequency counter. This is an audio signal generator, and I've got an oscilloscope. And that'll be the and I also have a DVM right here that I'll be using for some of these tests. So we're going to step through each test, and we will start out with the 50 watts channel into 8 ohms. Can it do it? Okay, so what you're seeing here, you're seeing both 8 ohm dummy loads being scoped, and we can read. We're looking at both channels. The yellow is the right channel, and the blue is the left channel. And at the bottom, we can read RMS volts. Okay, so we can see the RMS volts of the yellow and of the blue, and they're almost the same. So I'm just going to read one of them. We're going to turn up the input voltage, and we're looking at the output signal right here across the dummy loads. We're going to crank it up till we find clipping, and then find out what voltage that happens at. So there's clipping, right? I'm going to back it down to where there's no clipping, and we're at 21.9, 22 volts. Okay, so power equals V squared over R. We measure 22. 22 squared divided by 8 ohm dummy loads, and that equals 60.5 watts. 60.5, and so we get a big smiley face right there. Now, the next one's a little more challenging. The amp specifications spec out that 100 watts can be delivered into a 4 ohm load at 1 kilohertz with one channel driven. Now, this is a mysterious spec to me, because first of all, why with one channel driven? Who drives their amp with one channel? I mean, I don't know many people that listen to mono anymore. So this is not a practical spec. It doesn't really tell me how this amp will perform in real life situations where you have 2 channels being driven at the same time. I don't like that spec. I think the spec itself doesn't say anything. And they also say 80 watts, 4 ohms, 20 hertz into one channel driven. This one channel driven stuff, I find it impractical. So I am going to find out into a 4 ohm load at 1 kilohertz with both channels driven how much power this can deliver. I'm going to do it at 1 kilohertz and 20 hertz. Okay, so I had to parallel my two 8 ohms for one 4 ohm, and I had this monster over here I have one 4 ohm side and one 8 ohm side, so I'm using the 4 ohm side. So we have both channels into 4 ohms. We're looking at them on the scope here. We're going to find out where clipping is. Well, the protection circuitry is kicking on and off. Listen to that. Look at that. You can hear that? Protection circuitry on and off. So we reached some sort of current limiting of the amp right there into 4 ohms. So I'm going to gently crank it up to where the protection circuitry does not kick on. I'm going to back it down. Nope, protection circuitry kicking on. Okay, it's not on now. 14.3 volts on one channel, 14.8 on the other. So let's just call it 14.5 volts. Okay, so 14.5 squared divided by 4 is 52 watts. So right down here we're going to put in a 52 watts right there. Maybe I should try this one channel test just to see if there's bullshit going on there. But first let's... Ouch. Sorry, I had to do a hard cut right there. I just stepped on something really sharp that's still sticking out of my toe. And it's probably leftover wire from the construction of the kit. Aha! Ooh, it hurts. I'll deal with it later. Okay, so that was 1 kilohertz. Let's crank her down to 20 hertz. Okay, so got 20 hertz. Let's come back over here, take a look at the scope. I should have adjusted it. It's already into some clipping. So let me turn that down to where it doesn't clip. And what are we left and right child? We're at 7.2 and 7.29 volts. So let me turn up the volume a little bit. You'll start to see the clipping. Really, but it's one channel's hitting it before the other. And then there's the other channel. So turning it down to where there's no clipping on either channel. We're about there right now. Again, 7 volts. Yep. Okay, 7 volts. Okay, 7 times 7 is 49. 49 divided by 4 is 12.2 watts. So 4 ohm load, both channels driven, 20 hertz, you only get 12.2 watts a channel. Okay, we're going to go back up here and do the no bullshit test on the 100 watt into 4 ohms at 1 kilohertz. I've got 1 kilohertz back set back on the audio generator, and I'm driving one channel. I've removed the signal from one channel and I'm driving one channel only. You will see nothing but the yellow trace there. That's one channel. Let's find out where it clips and then back down. Clip, some kind of weird clipping, and then backing down and looking at, we're at 18.3 volts. Alright, so 18.3 squared divided by 4 is 83 watts. 83 watts. So we didn't get close to that 100 that's specified. So unfortunately, going to have to draw the steamy loaf right there. Alright, how about 80 watts, 4 ohms at 20 hertz? That's a much more brutal test. Let's go ahead and try that. Okay, got my 20 hertz set. Let's find clipping and back down. There's clipping. We're going to back down to where there's none visible. There it is, 8.38 volts. Okay, 8.4 squared divided by 4 of 17.6 watts. 17.6 watts. One channel driven, That's a far cry from 80 watts into 4 ohms. It's going to have to be just a slightly bigger pile of bullshit. Okay. Small signal bandwidth. Small signal bandwidth means it's not power bandwidth. Power bandwidth is the bandwidth at the negative 3 dB points at full power. Small signal is just at a smaller signal, such as, let's say, 1 watt. So I'm going to reconfigure. I'm going to get rid of the 4 ohm loads here, reconfigure back to 8 ohms per channel, and run this at 1 watt at 8 ohms per channel. Find out what the where the roll-offs are. Okay, so for small signal bandwidth, I have both channels driven, but I'm only going to be measuring one channel. I am driving both channels into an 8 ohm load at roughly 3 volts RMS, which is a little more than a watt. I've set at 1 kilohertz right now, and that 3 volts RMS is going to be a reference. And when it drops down to roughly 2.1 volts, that'll be the negative 3 dB point. The negative 3 dB points would be the voltage RMS times 0.707. So 3 volts times 0.707 is roughly 2.1 volts. I'm going to do that again on my calculator. 2.1 volts. Okay, so we're going to start going down. I'm going to start out with the lowest in frequency that I can go, which is about 10 hertz. About 10 hertz. And we can see we've already dropped to 2.6, so we have not reached our 3 dB point yet. As I rise up in frequency, I'm going to go up approaching 20 hertz now. 11, 12, and the voltage starts rising. Okay, so we're on the upward slope here, and we reach about, we're at 2.8, we're at 25 hertz, 2.9, so we're roughly at 3 volts right there at about 43 hertz. But I never was able to find the negative 3 dB point on the lower end because my audio generator doesn't go that low. So 5 hertz is perfectly believable. I'm going to say less than 10 hertz because I can't go any lower. Now let's try to find the upper 3 dB point. I'm at 32 kilohertz. Let me go back to 1K just to verify. Yeah, I'm still at 3 volts. Okay. Now we're at 10 kilohertz, and I'm going to start creeping up towards 20K. So we're still at about 3 volts. We're at 18K. There's 20K. 30K. Starting to drop. 43.5K. Okay, we're going to try to find that 2.1 volts. We kind of found it in this area right here. 2.1. We get a little lower. There's 2.1 volts, and we're at 97 kilohertz. So 97 kilohertz on the upper end. So that's greater than 50 kilohertz. So over here we get a smiley. Okay. We're now on to damping factor, greater than 80 at 1 kilohertz. Just a real quick note about damping factor. I made a video on this. It was kind of a self-indulgent video. It didn't really accomplish a whole lot other than getting into the theory of what damping factor is, describing what it is, and what it tells us about the amplifier. But if we view our amplifier as a voltage source with an output impedance, and I'll call that Z out, and that's intrinsic or inherent to the amplifier itself, and that should be very low. And then we hook our amplifier to a load, and I'll call that ZL for Z load. We want this internal resistance, or this output resistance of the amp, to be as low as possible for a couple of reasons. One is a speaker produces a back EMF. Okay, it's essentially a coil riding through a magnetic field, and especially woofers, they move through large excursions, and when they move, through a large excursion, and then the springs, the suspension, pulls that cone back to its toward its resting point. It generates a voltage. It acts as a generator, and it'll send that voltage back towards the amp. And to properly damp that, we'd preferably want that to go to ground, and to an AC voltage. A voltage source is ground, but it has to pass through this resistance first. And if this resistance is anything other than 0 ohms, which it will be, there'll be a little bit of a voltage drop there, and that'll allow for a little less control over the motion of that cone. That's a whole topic for another video. But the second reason is if this voltage is large, it could interact with your speaker and change its frequency response characteristics. Sometimes that's seen with tube amplifiers with a high output impedance. So we want that to be as small as possible, and damping factor is simply a ratio of Z out over Z load. Now Z load is going to be 8 ohms or 4 ohms, whatever your speaker is. And we want that Z out to be as low as possible. I'm sitting here talking this up, and I've got something entirely backwards, probably because I'm thinking and talking too fast. It's Z load over Z out. Okay, so damping factor wants to be large, and if Z out this is small, then this will be a large number. So, for example, if, just making some numbers up, if we know our load is 8 ohms, and we know our internal resistance, which is realistic, could be 0.1 ohms, then our damping factor is 80. Now, we can't directly get into the amp to measure this Z out, so we have to measure it indirectly through taking voltage measurements. And damping factor can be shown through derivation. It's a really easy derivation, as a matter of fact. It'll be voltage load over voltage no load minus voltage load. Load means with the speaker connected, no load means with the speaker disconnected. I won't get into the derivation, but it's pretty cool. It's really simple. And it derives from the fact that there's a common current flowing through both. So this is what we can do, and this is what I will do right now, just to see if I can come up with anything approaching the stated damping factor of 80 or more. Okay, I've set the audio generator to 1 kilohertz, and I've adjusted the voltage output. I'm taking the measurements using the Keithley. It's a pretty precise meter, and I'm taking the measurements directly off of the, I'm into the banana inputs of the binding posts. And I have a voltage, I'm doing it roughly at a watt, so I have a little more than a watt. I have 3.125 volts. Loaded. So now I want to disconnect the speaker. Now you can't do this with all amps, especially tube amps. You always want to have a load connected, but this amp it'll be just fine, and many transistor amps it'll be just fine to do that. So I'm going to remove the voltmeter, and I'm going to disconnect, being very, very careful not to short anything. Disconnect the speaker load, and I'm going to take another measurement. Not changing anything. 3.152. So you can see when I pulled the load off, the voltage went up, ever so slightly. I don't know if this is going to make a difference, but let's just see what we get. So we have 3.125 divided by, I'll go ahead and run this subtraction. Okay, so I ran the numbers with the calculator, and 3.125 divided by 0.027 is 116. So we get a damping factor of 116. That's at 1 kilohertz into an 8 ohm load, so we get a very happy face right here. The damping factor is higher than what's specified. I'll probably do the same with the other channel in a minute, but I won't show it on the video, because we've already seen one being done. If the results of the other channel on any of these tests that I do are different than the other, I'll let you know. If you don't hear from me, then assume they're roughly the same. Let's move on to harmonic distortion, spec'd out at 50 watts, which is pretty much the maximum of this amp. We learned it can go to 60.5, but it's almost the same as 50, into 8 ohms. Let me get that, I'll get that test set up going right now. Okay, for THD, I'm going to be using the Keithley. It's got a THD measurement setting. I'm going to be measuring THD. It's going to auto-select the fundamental frequency. It's going to find the harmonic, the fundamental harmonic, the input frequency. Forgive me. The upper harmonics are 6. I can select that to be various different harmonics, but I only want to factor in 6 harmonics. That's enough. The units will be in percentage. Okay, so there we are. We're spec'd out at 0.003% at 50 watts into 8 ohms. So what I'm going to do is I'm going to measure the output, the voltage across one of the resistors, one of the dummy loads, and I'm going to get it up to 20 volts. Why 20 volts? Because power equals V squared over R. R is our load, it's our 8 ohm. Okay, so the voltage I need to get across that 8 ohm dummy load will be the square root of P times R. 50 times 8 square root is 20 volts. When I reach 20 volts, I've reached 50 watts. Then I can bounce right over and take a THD measurement. So let's go ahead and get her up to 20 volts if I can. Bring her down to 20. Close enough. .004. Turn down that voltage. .004% THD. I'm surprised it's even that low, because I do have a low distortion audio generator there, but I didn't know the input distortion was that low. But apparently it is 0.004, and we get a big smiley face right there. Okay, input sensitivity next. I'm not sure why I'm even testing this. This is not really worth talking about, but the input sensitivity is just the they spec it out as 1 volt RMS on the input to achieve 50. Is that the spec? Let me go double check that. 50 volts out? There's no way. I must have transcribed something wrong. I'll go check on that. Alright, I was going to do sensitivity. I'm getting ready to call it a night. It's Friday night, and I'll pick up on these measurements tomorrow. Not that it's going to matter to you, because it'll all be one video, but just for my own knowledge, what I thought I'd do is a square wave test. And that's where we input. You're looking at both channels right now. Measurements across the 8 ohm dummy loads at 1 kilohertz. And a square wave test, it's 1 kilohertz input, and I am outputting about 3 volts. Turn it up a little bit. 3 volts RMS with respect to the square wave. And it's a nice, perfect, in both channels, a nice clean square wave. If there was a nice little handy chart that I keep here, down here, so I can remember, but if there was an issue with frequency response somewhere along the line, or ringing or other issues, a resonant point somewhere up there past the audio band, it would show up in the square wave. For example, you get these goofy looking square waves here with a treble boost, it'll look like that, with a treble cut like that, bass boost, it'll look like that, bass cut. And we get a nice, good, clean square wave. Just to give you an example, this is traditionally done at 1 kilohertz, but if we put in a lower fundamental square wave, something along the lines of, let's choose something like closer to 20 Hertz. Let's choose something like 20, 30 Hertz right there. And let's see if, now we're down close to the lower end of the lower 3 dB point. Okay, so you can see that the low frequency starts to fall away there because we're down near the lower frequency negative 3 dB point, and that's what the square wave looks like. Okay, and which looks similar to this one, base cut, and that's because our fundamental is 30 Hertz, and it's getting down to the like I say, it's starting to roll off there in the lower frequencies. But the 1 kilohertz square wave, which is typically what we use, looks fantastic. So if I had if I had a square wave test, I would put a smiley by that one, no doubt. Okay, be back tomorrow with the completion of sensitivity and input impedance. Neither one of them really need to be checked. I don't know why I'm doing that. It's really not necessary. Those are throwaway specs in a way. Yep. Okay. I think I'm going to call it a day on the testing here. So, in conclusion, I'll wrap up the video quicker than usual this time. In conclusion, looking at the, and I've already gone through this, looking at the power dissipation, this amp is an amp that needs to be used with 8 ohm speakers. You could use it with 4 ohm speakers if they're highly efficient, like my Forte 3s, but my Forte 3s are 8 ohms anyway. If you have a medium to low efficiency 4 ohm speakers, this amp is going to crap out, and crap out big time. And at a minimum, in the lower frequencies, as you can see, we could only, let me go down here to both channels driven. Into 4 ohms at 20 Hertz, this thing could only crank out 12.2 watts. So you're going to hear some noticeable distortion with inefficient 4 ohm speakers early on. So, first conclusion, this is an amp that needs to be used with high efficiency speakers or 8 ohm speakers. The bandwidth is fantastic. The frequency response looked pretty flat as I scanned through the frequencies there. Damping factor is fantastic. Harmonic distortion, at least into 8 ohms at 50 watts. And I think that was one, yeah, that was 1 kilohertz. Looked good. The Thd measurements could be done through the audio spectrum to the left and to the right, you know, lows and high frequencies. It changes a little bit, but I don't think I need to do that. I kind of did some THDs when I completed the last, or second to last video, I forget, and all that looked fine. And power bandwidth I was going to do, but I don't think so. Everything looks good. So we got a couple of steaming piles of bullshit on the 4 ohm specs right here when I actually drove one channel, alleged to be 100 watts into 4 ohms, only got 83. It really crapped out at 20 Hertz into 4 ohms. I only got 17.6 before severe clipping. That's a far cry from 80. Everything else got a smiley face. So, spec wise, it's a fine amp. Just be careful what speakers you use with it. Alright, I'm going to get a glass of wine. It's Friday night. Ciao.